Welcome to EPG Pathshala. Dear students, today I am going to discuss a very interesting and a recent topic of food processing, which I think most of us are not aware of. Yes, it is ohmic cooking, the new development in the field of food processing, wherein electric current is used to heat and sterilize foods. The foods processed by this method can be stored at room temperature for up to 2 years, retaining its taste and appearance. The heat energy is dissipated into the foods directly, resulting into uniform cooking. Let us go on a knowledge tour through this module to know about ohmic cooking in more details. Now, the objectives of this module are to understand the concept of ohmic cooking, to understand the principle lying under this method of cooking, to know about the various types of foods that can be cooked using this method, to learn about the different temperatures involved in ohmic cooking, to know about the different equipments and utensils required for ohmic cooking, to understand the merits and demerits of this method of cooking. Now we'll go a little bit into the background. Ohmic cooking and heating is a new development in the field of food processing for which the prestigious Queen's Award was granted. Ohmic heating is actually a technology of sterilizing foods so that it can be stored at room temperature for up to 2 years like other canned foods, retaining its taste and appearance. APV, the food and drink processing company, is now commercializing this technology. Ohmic heating was invented in Chester in the 1970s by the electricity company's research arm EA Technology and was licensed to APV in 1984. It was in 1988 that the first system for ohmic heating was sold. The process of heating fluid materials with the help of electrical current was patented in the 19th century. Further, in the 20th century, pasteurization of milk was done using electricity. The milk was passed on parallel plates having a voltage difference between them. Then trials were done on cooking of sandwiches using electric current for a fixed time. Shade used ohmic heating for blanching of potatoes to prevent the enzymatic discoloration. The technology disappeared in the subsequent years due to lack of suitable materials for electrode and controls. So the technology was only limited to electroconductive thawing. In the past 20 years, improved materials and designs for ohmic heating have been worked upon. A continuous flow ohmic heater has been patented by the Electricity Council of Great Britain and the technology has been licensed to APV bakers. This technology will definitely help the food industry in processing of liquid particulate foods in aseptic manner. In conventional processing systems, the liquid phase is heated which then transfers heat to the solid phase. In ohmic heating, food material is heated through internal heat generation system. So ohmic heating can very well be explained as a process where electric current is passed with an objective of heating the food materials. The energy is dissipated into the foods directly, so transferring heat by solid liquid interfaces is not required. Now we will see the applications of ohmic heating. In food processing industries, ohmic heating finds a large number of applications including sterilization, pasteurization, evaporation, dehydration, blanching, fermentation, extraction, peeling of fruits, heating of foods for serving. And the research data suggests that ohmic heating causes electroporation of cell membranes also. Peeling of fruits involves the use of lye, that is sodium hydroxide, which is a corrosive alkali. Ohmic heating can replace this old method of food processing. The diagram below indicates that ohmic heating is one of the methods of non-thermal food preservation, just like irradiation, ozonation, and high pressure processing. Now we will come to the principles of the figure which are being given below. The figure illustrates the principles involved in ohmic heating. In the process of ohmic heating, the alternating current is flown through a liquid particulate food system, also known as body, which acts as electrical resistance. AC voltage is applied to the electrodes at the end of the product body. The rate of heating in this process is affected by the square of the electric field strength and electrical conductivity. By adjusting the electrode gap and applied voltage, variation in the electric field strength can be created. However, the major factor affecting the process is the electrical conductivity of the treated food product. If a mixture of solid particulates and liquid are ohmically treated while regulating the process, the electrical conductivity of different phases of solids and liquids have to be considered. The electrical conductivity is directly proportional to temperature, suggesting that with increasing temperatures, ohmic heating is more effective. The heating pattern of the system becomes very complicated as it is dependent on a number of factors, including the difference in the temperature and electrical resistance of the two phases. To attain effective ohmic heating, the electrical conductivity of both the phases of the product can be adjusted by ionic content using different levels of salts as a source of ions. Ohmic heating process and equipments. Again, the figure given is a schematic of an ohmic heating process with continuous flow. In the feed pump hopper, the viscous product containing particulates is entered for processing. The product is then passed in the ohmic column through a series of electrodes where it is heated to the desired temperature. To achieve commercial sterility, the product is then entered in the holding tubes for a definite time. Lastly, the product is passed through tubular coolers into the storage tanks where it is kept till the process of filling and packaging is over. Configuration of most ohmic heating system consists of following three modules: heater assembly power, supply control panel. Now this is schematic of a continuous flow ohmic heating process. We will see the equipment design for this. Equipment design is a very important factor to be considered for the successful implementation of any technology. Inadequate regulation of temperature in the desired range, as well as the absence of inert material for electrode, were the causes for early failure of ohmic heating on a commercial scale. Moreover, the system was not sufficiently robust to adjust with the conditions of commercial production. Recent designs for commercial purposes contain electrodes which are located at positions like inline field, length of the product flow path, or cross field that is perpendicular to the flow as per distribution of electric field strength. Now we'll see the electrodes. A wide range of electrode material from aluminium, stainless steel to graphite were used in earlier designs of ohmic heaters. For food processing, the electrodes must be carefully designed and a high standard hygienic design is required. The electrolytic effect, which brings about the dissolution of the metallic electrodes, was completely neglected in the previous designs of ohmic heaters. Food product contamination problem was seen due to the absence of suitable electrode material, as the material technology was not developed at that stage. Now, with recent advancement in technologies, a suitable electrode material which is food compatible and the use of correct current density has ruled out the contamination problems. Utilizing high power frequency is the one of the different way to solve this problem, as there is no metal dissolution at alternating frequencies above 100 kHz. Now about control, the first scientist who emphasized that it is very important to control the ohmic heating technology was Getchell. At that time, significant developments in the field of semiconductor technology occurred, which led to the sophistication of control equipment. In continuous processing method, problems occurred when a single electrode pair was used to heat food material under different temperatures. The process is easier to control if in place of single electrode pair, a multiple set of electrodes is used. Biss et al. Suggested the necessity of development of a feed-forward control scheme. For this scheme, a general idea of characteristics of the system is needed. Now we will see the commercial equipment. The commercial unit of APV Baker is used for the heating of liquid particulate mixture. The Electricity Control Council Research Centre of UK developed the process of ohmic heating and then licensed it to APV Baker. Here it took the shape of a commercial system. After pumping the food to be processed, flows through a vertical pipe which has a number of cylindrical electrodes which are further connected to three-phase electric supply. When the electric current flows through the food material, it is rapidly heated to the temperature of sterilization. The sterilized food is then passed to a holding section and then finally to an aseptic packaging plant. A much greater degree of control is possible in ohmic heating than other techniques due to the use of multiple electrodes and a uniform electric field. The packaging process is equally important in maintaining the sterilization done by ohmic heating process. To eliminate polarization and contamination, specially developed material is used for electrodes. For the food products having particulates up to 25 mm size, the temperature for sterilization is maintained up to 140 degrees centigrade and the heating time is kept at less than 90 seconds. Then the food product is cooled in holding tubes to ambient temperatures with a period of 15 minutes. The entire process is automatically controlled with a programmable logic controller. The processing time here is significantly shorter than the typical in-can sterilization technique where 2 hours processing is required. As all the previous attempts of commercialization failed due to problems of uneven heating of the product, and electrode degradation, APV has conducted research on some key areas of the technology, like arrangement T design of electrode safety, standards for such equipment validation, procedures for proper sterilization of food products, research related to any toxicological effect on food products. On the basis of these studies and trials, a report was prepared and submitted in 1991 to the Advisory Committee in UK for Novel Foods and Processes. For this report, the Institute of Food Technologists begged the Industrial Achievement Award. The report was for the approval of the APV commercial Ohmic heating system for the production of ready-to-eat meals with low acid content in United Kingdom. The 5 kW Ohmic heating system APV Baker Limited product specifications and process parameters for specific products. The heating of a food system ohmically is influenced by particle orientation in contrast to conventional heating, in which little difference in heat transfer is expected due to changes in particle orientation. Particulates are the center points around which an ohmic heating formulation is made against conventional heating, where a very little difference in heat transfer is observed with changes in particle orientation. D. Elvis et al. Conducted a research and found that the heating of potato particles, which were identically shaped, differed on the exposure of the particles to the electric field, that is, whether they were aligned, parallel, or perpendicular to the electric field. According to them, this difference was due to change in the electric field as well as in the equivalent resistance of overall circuit. A practical limitation of particle shape and size might be expected when both the heating and cooling stages are considered. Thermal conduction controls the cooling of particulates, as it has been observed that the center of large particles cool down gradually and become overcooked when the cooling is prolonged. With suitable product and process control, different types of food products can be successfully processed. Standardizing the combination of particulates as well as the liquid phase will give good particulate texture on uniform heating. To get good suspension of particulates, viscosity should be checked at various temperatures. This will also help in liquid particle interface heat transfer. Overall product specifications should be taken care of, like particle shape, size and orientation, its pH and viscosity, its specific heat and thermal conductivity, the solid liquid ratio of the product, and lastly its electrical conductivity. These are very important for successful processing procedure. Process design, where a complete description of the critical processing conditions is described, is equally important in production of good quality products. This includes initial temperature and exact temperature of the product, batch formulation procedures, solid loading levels and flow rate. These parameters will not remain the same for all types of formulations and systems, and it is also necessary to understand their impact on heating behavior. Time temperature monitoring techniques for locating slowest heating regions. Scientists are doing research in the field of ohmic heating, and they have documented that during an ohmic heating process, particles do not heat uniformly because of difference in their physical properties as well as due to the non-uniform nature of the electric field. It is equally important to know about the time and temperature history of the coolest point of the food mixture, which is exposed to ohmic heating. It is assumed that any disparity in the temperature profiles of the particulates minimizes on agitation of a continuous processing system. There are not much evidences to indicate the temperature inside a particle and the changes that take place with time. It has been observed that a particle with homogeneous electrical conductivity heats faster than the liquid phase in which it is suspended. The coldest spot is on its surface and the liquid will be colder than the particle. It is important to find out the location of the slowest heating region as its thermal lethality has to be ensured. To determine the processing time, this is the prime factor. There are some conventional invasive techniques to measure the heating of food systems like thermocouples and fiber optic probes. For understanding and controlling ohmic heating, a non-destructive and non-invasive technique that can be used is the MRI mapping technique, which is used to monitor and validate the temperature for ohmic heating process. This technique can be further improved by using it to collect data for different processing conditions and different product specifications. Now we will go into the advantages of ohmic cooking. As per the researches done in the field of ohmic heating technology, the advantages can be summarized like this. The food material is heated by internal heat generation with no limitations of conventional methods of heat transfer. Non-uniform cooking seen with microwave heating because of limited dielectric penetration is not seen in ohmic cooking. Moreover, heating here takes place volumetrically and the product is not required to face a large temperature gradient within itself while heating. It is impossible to achieve higher temperature in particulates than liquid in all conventional heating methods. It is only possible with ohmic heating where working temperatures can be raised up to 180 degrees centigrade. Ohmic heating results in minimal mechanical damage as there is a low risk of fouling and surface burning on heat transfer of the food product. Higher product yield and less product loss is the key benefit of this method. In ohmic heating, electric current is passed which heats the food like the bar on electric fire. Most foods can conduct electricity as they contain water with dissolved ionic salts. Ohmically sterilized food is not overcooked as each part of the food heats up at the same rate. This method is energy efficient as more than 90% of the electrical energy is converted into heat energy. We can say this is the only method that can handle highly viscous food products. Ohmic heating is a very simple process for the handler as it can be controlled with instant switch on and shut down. The equipment for ohmic heating has a very easy maintenance and a nominal maintenance cost as there are no moving parts in it. It is an environment friendly system with no fumes, no smoke or burning of fuels like wood or charcoal. In ohmic heating, flavor and vitamin retention is better as compared to traditional methods. Again, in ohmic heating, microbes are thermally inactivated, making the food aseptic. During ohmic heating, operating at low frequency, that is 50 to 60 Hz, a mild electroporation on mechanism may occur in which pores across cell walls are formed by the electrical charges. In conventional sterilization process, low acid products have to be heated to at least 121 degrees centigrade for a minimum period of 3 minutes. Overheating the liquid makes the outer part of the food soft and vitamins are also destroyed. This does not occur in ohmic sterilization of such products. The ohmic method is successful with any food that is a conductor of electricity that can be pumped through the system and has food piece size of less than 1 square inch. Examples of such product can be stews, sauces, soups, pasta, curry dishes and pie fillings. The fruit remains whole and firm. In the case of strawberries, either canned or defrosted fruit. Although preserving food ohmically is costlier, but its subsequent cost is less as such products do not need storage in freezers or refrigerators. It takes less time to process the food and the quality of the product is better than canned products. In conventional methods of cooking, heat is transferred to food through conduction from hot surfaces. This only is the reason of slow rate of cooking of products having large particle size. In ohmic heaters, food can be heated from within by using the food's own electrical resistance for the generation of heat. The ohmic processing units produce products of a superior taste, color, and nutritive value due to their unique method of heating with a good regulation of time and temperature. Moreover, the energy efficiency is in excess of 95%. The result is enhanced cooking rates as well as good product quality. The diagram given depicts the comparison of cooking times of various food items by ohmic method and conventional methods of cooking. Now, disadvantages of ohmic cooking. The disadvantages of ohmic heating are linked with its electrical heating mechanism. The rate of heat generation may be affected by heat channeling, particle shape and orientation, complex coupling between temperature and electrical field distributions, and electrical heterogeneity of the particle. All the above mentioned factors are enough to make the process a complex one and thus leads to production of non-uniform temperature. This makes the process difficult to monitor and control. Now we will summarize. Ohmic heating can be explained as an advanced thermal processing method in which electric current is passed through food materials in order to heat them. In this process, the energy is dissipated into the food particles directly and there is no need to transfer heat either through solid liquid interfaces or inside the solid particles. Ohmic heating finds a number of applications for preparation of food as well as for food processing in day-to-day life. Besides heating of foods to serving temperatures, it can be used for a number of processes like pasteurization, peeling of fruits, blanching, dehydration, extraction, fermentation, etc. Researches done in this field suggest that the electric field applied in ohmic heating causes electroporation of cell membranes besides heating of food. Thank you.